So you all just finished getting the orthonormal diagonalizing matrix Q for one of the examples that we had in the book. So we'll be continuing from there. This was the orthonormal matrix Q, which is simply the a matrix made with the eigenvectors normalized. Right, so let's go to example 3. Right, so this time I'll just use the values given. We have A equals 5, -4, -2, -4, and notice it's symmetric about that. -2, -2, 8. So we know this has to be -2, so it's symmetric about that axis. So it fits the pattern we noticed last time about symmetric matrices. So we also do all the eigenvectors and everything. Our characteristic equation would be -t cubed plus 18t squared minus 81t. And that's going to equal -t minus 9 squared, which means the eigenvalues are equals 0, 9, and 9. So there's 2 9s, interestingly enough. Our eigenvector is 2, 2, 1. And this is for E0 is spanned by this vector. E9 so the book says A minus 9i. So using the lambda equals 0, we get that. For lambda 2, 3 equals 9, it's saying that's rank 1. So the spectral theorem guarantees it's two-dimensional, that we get 2 of them. I don't remember the spectral theorem indicating anything like that, but we know that this book skips a lot of steps, and apparently explanations, at least, is not very clear sometimes. So, but this gives the eigenvectors v2 equals -1, 1, 0, and v3 equals -1, 0, 2. So we want an orthogonal or orthonormal basis. We must use the Gram-Schmidt process. Right, so I have to review Gram-Schmidt. So gram, like the metric unit, Schmidt, the vector W3 equals V3 minus the projection onto W2 of V3. So that equals -1, 0, 2 minus 1/2 -1, 1, 0, which equals -1/2 -1/2 2. We multiplied everything by 2. Now we have -1, -1, and 4. So that means that V1 is orthogonal to W2 is orthogonal to W3. I should say X1. We needed to project 3 onto 2, or at least take the V3 and then V3 projected onto V2. We made that orthogonal. So to make the orthogonal diagonalized matrix, they made them into unit vectors and made a vector. Right, so I'm gonna have to work on that one. I have to remember the Gram-Schmidt. We conclude this discussion with a comparison to our study of projections in chapter 4, which if we write out A equals, I'll start it like this, A Q equals Q diagonal. So as always, the chevrons on the outside, the matrix on the inside. So A equals Q diagonalized Q inverse, which equals Q diagonalized Q T. This is the so-called spectral decomposition of A. Multiplying by a symmetric matrix A is the same as taking the weighted sum weighted by the eigenvalues of projections onto the respective eigenspaces. This is indeed a beautiful result with many applications in higher mathematics and physics. Right, so I'm still not clear about what's going on, but we'll see if we can catch it up along the way. So they're doing some kind of conic thing, which I'll skip for now. Cones and ellipsoids. So let's take a moment and look at the Gram-Schmidt. Right. So this will be the last thing, Gram-Schmidt. Maybe what I'll do is come back. So I'll come back in a bit and we'll start with the Gram-Schmidt process, and I'll just name the video Gram-Schmidt as the backdrop for the spectral theorem. So I'll see y'all in a bit.